Alright, so we begin part 3 of lecture 7. So we want to define how to work with the algebra, if you will, of matrices of differential forms. So basically we take a M by R matrix of P forms and a N, let's see here, no, R by N matrix of Q forms. P and Q meaning, like, you know, they could be 0, 1, 2, 3, or 0, 1, 2, 3 forms if we're working in R3, but the definition I give here is more general than that. And basically you just multiply these matrices of forms just like you'd multiply an ordinary matrix. So in particular we define A wedge B, okay, the ijth component of this. So I'm promoting the notion that we can do matrix theory just the same, whether we have numbers or whether we have differential forms. Well, I would advise against dividing perhaps, but you know. Anyway, silly comments aside, this does provide us a good definition to work with here. We'll find that we derive all the things that O'Neill claims. So A wedge B, the ijth component, is just the sum of the wedges with summed over k. This is I don't know if you've seen it before or not. Well, I think most of you have, but this is exactly matrix multiplication with the product replaced with a wedge product. All right. And so that gives us the wedge product of two matrices. They're multipliable, just means that the k can be summed over. All right, so the column index here has to match the row index there. Anyway, also likewise, we define, you know, the exterior derivative of A. That is a new matrix, which is defined to be, we just exterior differentiate component-wise, all right? So that's, of course, that's a matrix of P plus 1 forms. And we also have standard things like A transpose, for example. Ij would just be equal to Aji, so we can also do transpose. But, I mean, this is a M by N matrix of P forms. This is a N by M matrix of P forms. So there's your definitions. Now, probably worth our time to go through an example here. So let's do that. Let's see here. What if I have dx, dy, dz, I suppose we're in a four-dimensional space, dt, and I take the wedge with, I'm curious what happens. I'm going to do the opposite order, dt, dz, dy, dx. I'm curious what happens here. Oh well, that wasn't quite what I wanted to do. We'll do it anyway. Alright, so what we get? We should get a matrix of two forms. So what we get is, I'm going to write it like this. So we'll get dx wedge dt plus dy wedge dy. I guess I don't really need to write that, right? Because dy wedge dy is 0. And then we get dz wedge dt plus dt wedge dy. And then we get dx wedge dz plus dy wedge dx. And then we get dz wedge dz, which I didn't really need to write because of course that's 0, plus dt wedge dx. Alright, well, that was interesting. Not really what I wanted to do though. Let's try it again here. So what if I took dx, dy, dz, dt, and I just wedge it with itself? What would happen? We know that the one form, wedge of one form, is automatically what? It's automatically 0, right? How about a matrix of one forms wedged with the same matrix, right? This is A wedge A. If this is A, right? Probably it won't be 0. Let's see here. So dx wedge dx is 0. I'm not going to write that. What we get is dy wedge dz. We get dz wedge dx. Plus dt wedge dz. Interesting. And let's see here, dx wedge dy. Plus dy wedge dt. dz wedge dy plus 0. Curious. Anyway, as you can see, not 0, right? So things we can say about one forms don't necessarily apply to matrices of one forms, kind of just like numbers. All right. Finally, let's see here. If I have x squared dy, and let's see here, z dx, and then dz, and finally z cubed dz. We can calculate the exterior derivative of such a form. We would get, so you get 2x dx wedge dy. See here, dz is 0, d squared is 0, right? Up here we get dz wedge dx, and we get 3. I'll just write it out, but 3z squared. No, it's 0. 3z squared dz wedge dz. So there's an example of exterior differentiation. Anyway, let's just go ahead and get past this example and look at something slightly more interesting. And that is the product rule. Proposition 2.6.5. All right. If we have a pair of multipliable matrices, and let's say m by r, matrix of P forms. All right. And B and R by N, matrix of Q forms. Then, if we take the exterior derivative of the wedge product, A wedge B, we get dA wedge B plus minus 1. So this is what's known as a graded Leibniz rule. The grade given by the degree of the forms comprising A in this case, minus 1 to the P, A wedge dB. And there you go. That's the product rule for matrices of forms. Now let's work it out. I mean, I suppose if you dig down far enough, it's the product rule in Calc 1 plus algebra, but I'm not sure we'll get quite that far. So dA wedge, so that's equal to the exterior derivative of the sum over k aik wedge b kj. All right, but that is what? That is the sum over k of d of aik wedge bkj. Oh, I guess the thing we should remember is we already proved the graded Leibniz rule for forms, right? This is for matrices of forms, but we already have a product rule for just forms alone, and so that's daik wedge bkj plus minus 1 to the p, because aik is, I haven't used this notation enough, but I really should. It's a p form. It's in here. Now, I guess I'm really doing this for Rn, truth be told, but I mean usually R3. Anyway, so minus 1 to the p, aik d bkj. But remember, that is really parentheses dA ik wedge bkj plus minus 1 to the p sum over k aik parentheses d bkj. Just to emphasize, it's the matrix of forms dB. It's the matrix of forms dA. Anyway, that's exactly dA wedge b plus minus 1 to the p a wedge dB. And there you go. There you have it. Product rule. Now, this is very, very interesting as we think about what it says about orthogonal matrices, for example. Well, I guess orthogonal matrices themselves are not that interesting, but how about the attitude matrix, right? What do we get to say about the attitude matrix? Well, it's P assigns to a matrix AP, right? Where, if I'll put the point dependence just for a second here, AP transpose AP is equal to I for all P in R3. Now, so we usually just write this, A transpose A equals to I. Sorry, I refuse to write the transpose on the other side like O'Neill. I'm sure there's a good reason for it, but nobody ever convinced me of it, so I'm writing my transpose there. Anyway, so okay, great. Well, if you have this, then we can. I mean, these are zero forms, right? It's a of p goes to a of p is a matrix of functions, a matrix of zero forms, really. So I could write this, just to be pedantic, A transpose wedge A equals I. I mean, you can do that. I mean, but you could argue, well, you don't need the wedge there. Well, fine, true, but just, I mean, this works, this derivation right here holds for functions just as well as honest to goodness genuine. Well, a function is a genuine zero form. All right. Anyway, if I differentiate this, all right, I have dA transpose wedge A, let's see here, plus A transpose wedge dA equals to 0. Well, that's interesting. So that tells me then what? That tells me that dA transpose wedge A is equal to minus A transpose wedge dA, right? But what else does that tell me? Well, if I multiply both sides of this, I mean, there's two different ways you can go from this, all right? Two things I can get from this. I can multiply by, let's say right multiply by A transpose, right? If I do that, that gives me dA transpose, because I get A transpose, which is the identity. All right. On the other hand, if I left multiply by A, that gives me a minus identity here, so bring the solve for dA, okay? that gives me dA is equal to minus A wedge dA transpose wedge A. So there you go. These are kind of neat formulas, I think. I mean, take them or leave them, but there they are. Now there is a little lemma that I just used, which is that dA, or I guess it's not really about dA. It's just that any matrix B wedge the identity matrix of the right multipliable size is just the B again. So you notice that you've got a P form, or a Q form, I suppose, a 0 form, and then a Q form again, so at least it makes sense. Great. I don't know. I guess I could spend a lot of time talking about these things. I think these are very interesting, very fun. But the real reason we talk about the attitude matrix and these matrices of forms is what follows. All right. So it turns out that there is this very convenient method, right, of calculating the connection from the attitude matrix as follows. So here's the theorem. Let A be the attitude of a frame, you know, E1, E2, E3 as usual, and omega ij the connection form. Forms, I suppose, in my current notation. Then omega is equal to the exterior derivative of the attitude matrix wedged with the transpose of the attitude matrix. Alright, so go through the proof of this. Actually, there's nothing really dramatic in this proof, but it's easy to get lost, in my experience, in this one. So let's just set the notation. E1, E2, E3 a frame, Aij defined as follows. So Ei is equal to a sum, right? K equals 1 to 3 of A, Ik, Uk. Alright, just to be pedantic here for a second, I mean, just to be explicit, that's AI1, U1, plus AI2, U2, plus AI3, U3. That's just what we said before when we talked about the attitude matrix, alright? You should also recall that omega ij acting on V is simply covariant derivative in the V direction of EI dotted with EJ. Alright, we need that too, of course. So we start with our omega ij of V. And so that's the covariant derivative of V, in the V direction rather, of the sum. K equals 1 to 3 of A, Ik, Uk dot Ej. Okay, so far all I've done is just to expand EI in terms of the attitude. Oh, sorry. Let me not. Let me just calculate rather than try to figure out some new fancy way to do it. I mean, there's probably some shorter way than what I am about to write, but anyway, I'm not trying to reinvent the wheel right now. Okay, so pull the sum out, and what do we have? We've got I should really stop. Well, whatever. So covariant derivative of v. Then I use the product rule. I'm just going to write some over k. We know where it goes from. So that's v acting on aik, uk, plus what? Plus aik, covariant derivative in the v direction of uk. I don't guess I really need to write that down because we all know that the Cartesian frame is very boring. 0. And so this gives me some k vaik uk dotted with what? Well, some. I'll use L. L equals 1 to 3 of A JL UL. So I'm just using the attitude matrix to expand the J. Great. Now, what happens with this dot product is I have a sum over K and L, and I've got the AIK, AJL, UK dot UL. Of course, we know what happens there by the orthonormality of the Cartesian frame. This, of course, is just Kronecker delta KL. Kronecker delta KL, you can get rid of one of these. I'll get rid of the L, so that will nix that, and that basically sets K equals to L in the next step. So we got sum over K of the, what we got here? A, I keep the K, A, J, lose the L by the Kronecker delta, the previous step. But what do we have here? Well, you should recognize that this is exactly dv. Well, I guess it's hard to recognize it because well, oh, dv, listen to me. That is dA ik acting on v, and that's a transpose kj. Aha, matrix product. So I can drop the k because it's the matrix product. What I really have is dA wedge A transpose the ijth component of that, and that's acting on v, right? I mean, I'm defining a matrix of forms acting on a vector field to be each component form acting on the vector field put together in a matrix in the natural way, right there. But anyway, you can see then, with that definition given, or settled, or I wave my hand at it, let's see here, you can see that we have exactly the claimed result. So in other words, we can calculate the connection form simply by taking the exterior derivative of an attitude matrix and taking the wedge product with the transpose. That is pretty cool. Well, anyway, I think it is. Two of my favorite things, matrix calculation and differential forms, all together in one happy combination. So an example, an easy example, would be something like A equals to cosine theta sine theta minus sine theta cosine theta 0, 0, 1, 0, 0. This, of course, is the attitude matrix of the cylindrical coordinate frame. So you can see we get dA, pretty easy, minus sine theta cosine theta minus sine theta minus, was there a minus? Yeah, there's minus. Minus cosine theta 0, 0, 0, 0, 0. And I just took the liberty of factoring out the d theta. Okay. With that notation, we can calculate dA wedge A transpose. All right. And so that gives us minus sine theta cosine theta minus cosine theta minus sine theta 0, 0, 0, 0, 0. We can bring the d theta outside, because if you think about it, it's just going to be everywhere, and if you think through it, you'll see what I'm doing is not unreasonable. All right. Sorry, I guess I'm kind of ruining it by doing that, but oh well. So, if you believe in omega 1 being 0, you don't have to calculate this, but I always find it's comforting to see that we get sine times minus sine times cosine, minus sine cosine, plus sine cosine, 0. Great. All right, and then minus cosine squared, minus sine squared, that's a minus 1. And then, of course, we get 0. And then we get minus, sine squared plus cosine squared, we get 1. We better get antisymmetry there, right? That better be 0. And then the rest of them actually turn out to be 0 when you multiply them out. So, therefore, we find the connection form for the cylindrical coordinate frame is just 0 d theta minus d theta, 0, 0, 0, 0, 0, 0, just like that. There's an example. A less simple example, an example that has given me some fits lately, is the attitude matrix for the spherical frame. So for the spherical frame, I had an error in my notes originally, but I fixed it now, thanks to the help of Daniel Fries. Let's see here, cosine theta, sine phi, sine theta, sine phi. Don't worry, I'm not going to do the whole calculation here. Just get us started. So basically the trouble was I had a minus sign here that was wrong. Now this is the spherical attitude for the standard math spherical coordinates, okay? It's not the one for the spherical coordinates given in O'Neill. But if you take this, all right, then you can calculate dA. I'll do that. So like dA here would be minus sine theta, sine phi, d theta, plus cosine theta, cosine phi, d phi, then we've got, let's see here, cosine theta, sine phi d theta, plus sine theta, cosine phi d phi, minus sine phi d phi, minus sine theta, cosine phi d theta, minus cosine theta, sine phi d phi, cosine theta, cosine phi d theta, minus sine theta, sine phi d phi, minus cosine phi d phi 0 minus sine theta d theta minus cosine theta d theta. It's actually probably a good idea to separate these into two matrices and like just factor out the d theta and factor out the d phi. I found that to be useful when I calculated it. Anyway, if you take this, believe it or not, and you calculate the connection form by taking dA and wedging it with A transpose, what you'll get, and I've checked this, is 0 d phi sine phi d theta cosine phi d theta 0. And then by antisymmetry we already know what's going to happen. Although that's a good check on your calculation. If you get not oops, that's supposed to be theta. You should have antisymmetry of the connection form matrix, right? And so there it is. That's the connection form for the spherical frame. Anyway, that's all I have for this lecture, I think. So next time we will pick back up with the question of what's the dual basis to the, well, dual frame, but we call it coframe. So we'll talk about coframes to a given frame, and we'll see that this whole calculation can also be connected to the coframe through these so-called structure equations of Cartan. Anyway, again, the matrix and the combination of matrix algebra and differential forms allows us to kind of get through that stuff with relative ease. We've actually done the hard part already here. Anyway, thanks. Sorry for being so pokey today.